So the final lecture, I can see jubilation in those eyes from me on Laplace transforms and the applications to the linear time invariant systems. Now we continue studying responses of common systems, and today we do a little bit of electrical engineering because the system for which it is most intuitive and easy to understand is in fact an RLC circuit of the kind that you would see if you were chemical engineers in electron paramagnetic resonance, nuclear magnetic resonance, MRI, and in a few other places where you have resonant circuits that are tuned to a particular frequency. So item 1 on our to-do list today is series RLC circuit. And as the name suggests, this is something quite simple. We just have a resistance that is in sequence with some inductance, which is in sequence with a capacitor, and all of that is driven by some voltage source. So that's our R, that's our L, that's our C, hence the name of the circuit. And let us think about what this thing would be doing. If we turn on the voltage source, of course the circuit is strictly speaking broken here, but what will happen is that this capacitor will begin to charge, right? The relationship between the charge on the capacitor and the voltage applied to the sides of it is in fact proportionality, right? So the capacitance is the coefficient, but as the current flows it will have to pass through the resistance, and more importantly this inductance, where the voltage across the inductance is proportional to the derivative of the current. And so we start seeing response properties in there. In particular, if this L exceeds a certain threshold value and the voltage change is very sharp, what will happen is the inductance will start interfering with the charging process and cause voltages to overshoot, charges on the capacitor to overshoot what would be otherwise the equilibrium value. But of course, if we turn this source on and hold it steady for an infinite time, then the situation must settle down to the case where the charge on the capacitor is proportional to the voltage difference across its terminals. Okay, so let us go through a little bit of electrodynamics. You may or may not have had it. I will simply just introduce and explain what we mean by the various terms there. We start from a common simple observation. If we call this voltage source Z, an integral over the voltage over any closed loop must be 0. This is because the voltage difference between two immediately adjacent points on any circuit is 0, and if you integrate it over the closed loop, there must be a voltage balance, which means that the source voltage as a function of time here must balance out. It must be equal to the voltage across the resistor plus the voltage across the inductor plus the voltage difference across the capacitor. And this is the fundamental law called Kirchhoff's voltage law, if you haven't had it in your chemistry courses. Then, of course, for the resistor, we have Ohm's law, which relates the voltage across the resistor to the current that resistor sees. So VR as a function of time, as per Ohm's law, is resistance times the current as a function of time. And I put everywhere T in brackets because in principle we can have input voltage variations. Okay, so that is the standard Ohm's law. Then inductor equation, the voltage difference across the inductor, again is a function of time, is the inductance times the derivative of the current. And of course the current is common to this circuit. And finally we have the current through the capacitor, so I of t As per the definition, it's the capacitance times the derivative of voltage at C as a function of time. Okay, so what we see here is we can put VR here, we can put VL there, we can put VC derivative, notice here, there, and then the final thing to observe is as charge on the capacitor goes, the current is the derivative of the charge, right? So finally I of t will be dq by dt. Okay, so we put all of that there and we express the final equation in terms of the charge on the capacitor as a function of time. I will not go through the boring substitution process, it's quite standard. What we get is d2q by dt squared is plus r over L dq by dt plus 1 over LC q of t equals 1 over L v source as a function of time. And so this is a second order linear differential equation where the state variable is the charge on the capacitor and the input is the voltage that is delivered by our voltage source. So suddenly we can see an instance of our system response and we can now begin looking at it in the Laplace domain and finding out what the various modes here might be. Okay, the standard Laplace transform here, we assume that the initial condition, right, so q of 0 was 0, and that allows us to just straightforwardly visually translate all of the derivatives into the Laplace domain. So we have s squared q of s from the second derivative plus r over L sq of s from the first derivative here plus 1 over LC, then q of s equals 1 over L and then voltage in the Laplace domain. V source as a function of the Laplace variable. Fine, we can just do the standard solution here and we can express the charge as a transfer function multiplying our input. So I will take q of s out of the bracket here and push it over to the denominator on the right hand side, and we are going to get, so q of s is capacitance at the top, then tau squared s squared plus 2 zeta tau s plus 1 times vs of s, where this tau is root LC, the response time of the circuit. If you did such circuits before, you will recognize 1 over the frequency of it. And then zeta is the damping variable, R over 2 C over L. Notice here that it is proportional to the resistance, so it is responsible for the damping of whatever current is excited in that circuit. Okay, and after the dust has settled, we have this. Notice the capacitance in the numerator, and of course that is the ability of our capacitor to hold charge. And so when we are looking for the charge that's eventually going to happen here, capacitance acts as the amplification coefficient for it. Okay, let us use our by now considerable knowledge of Laplace domain system analysis to figure out what is going on here. Firstly, we need to find out the type of dynamics here, and that is determined by the denominator here, namely its roots. If we solve this quadratic equation for s, we will have two roots. And as you remember from the previous lecture, if they are two real roots, then we have exponentials in the solution for the system. If they are equal, identical roots, then we still have the exponential, but if they are two complex conjugate roots, then we would have sinusoidal oscillations, possibly damped, and this is what I have shown you in the previous lecture. Okay, so our input now will be a ramp, so ramp input, not ramp, step, so step input, for which the Laplace image is the amplitude, which in our case will be some input voltage over S. So we are stepping our input from 0 voltage to some fixed value V in, and the Laplace transform of a step function is 1 over S, hence V in over S. So our Q of S under that input is going to be exactly the same thing, so tau squared S squared plus 2 zeta tau S plus 1, and then V in over S. Let us do two things. Firstly, let us analyze the denominator in the transfer function, and secondly, once we've done that, let us invert the Laplace transform and obtain the specific equations for the charge as a function of time in this circuit. Okay, so discriminant here, right, b squared minus 4ac, so we've got that here, so that is 4 psi squared tau squared minus 4 tau squared, and that is 4 tau squared, and then zeta squared minus 1. Tau is by definition positive because of this root. The sign of the discriminant is therefore determined by which side of 1 our damping parameter is. And notice what we have here. In a typical electrical circuit, it's very hard to alter the inductance because the geometry of, for example, the NMR probe coil in NMR spectroscopy is fixed. What you can change is this resistance, and of course there are easily tunable capacitors available on the market. So depending on the numerator here, resistance and capacitance, we can alter the value of the damping coefficient. Resistance predictably damps everything, and somewhat less intuitively capacitance does as well, because it takes longer time to charge a capacitor if the capacitance is greater. Okay, so we will have here 3 special cases. So firstly, a situation where this zeta is greater than 1. This is called overdamped, for reasons which will become clear after we analyze all of the other cases as well. And I will not bore you with the explicit inverse Laplace transform of that. I will simply just write it down, and then we will analyze what is happening there. So Q of t back in the time domain is C times V in, and this is the asymptotic value of the charge, and of course that comes from the definition of the capacitance, right? It is connecting the voltage that you apply, voltage difference that you apply to the terminals of the capacitor, to the charge that is accumulating within that capacitor. So it's 1 minus tau 1 e minus t over tau 1 minus tau 2 e minus t over tau 2, and then tau 1 minus tau 2, where these taus 1 and 2 are the tau that we have, the response time here, and then zeta minus plus root zeta squared minus 1. So what is happening here, notice, is the exponential fade in to the value that is prescribed by the electrostatics. It is not reached immediately. Of course, for any finite voltage that we put in, the capacitor will take time to charge, and decharge by dt is a first order process, and then of course the result will manifest itself as an exponential crossfade. Okay, if we start plotting this, so I will plot q of t as a fraction of the asymptotic charge that we have here, starting from 0, because that was our initial condition, as a function of relationship between our time and the time constant. So we have normalized variable on the output, normalized variable on the input. So the graph we are going to plot is in some sense universal for any such system, because it doesn't actually depend on any particular parameters. It's in dimensionless coordinates, so to speak. So if we have our zeta that is large, the process will be slow. So we have slow exponential accumulation, and it will reach the asymptotic value of 1. Right, so that is 1. If we start increasing, so that you have it in your handout, is zeta equals 3. If we start increasing, decreasing the damping parameter by decreasing either the resistance or the capacitance, what we're going to have is it'll start accumulating the charge faster and faster until we get to a situation where we are on the borderline with respect to that discriminant. So that will be our zeta equals 2, and this is the best we can do. So zeta equals 1. And of course, ideally, in all sorts of electrical circuit design, we would like the circuit to respond as quickly as possible with minimal trouble. But it would seem that at this point we can no longer make it charge that cap faster without something mathematically fundamental happening to the discriminant, and therefore to the entire solution, which would stop being just a bunch of exponentials like here and start being something else. For that reason, this situation where zeta is equal to 1 is called critically damped. Right, so the least damped without something qualitative beginning to happen. So that is the second term that I would like you to take away from this lecture. And so let us now go into that regime. So this was our regime A, this is our regime B. Let us go into the third regime where the discriminant is in fact negative and the roots are complex. Once again, I will skip the giant pile of arithmetic that comes from elementary primitive fraction expansion of that cubic that you have in the denominators and followed by the inverse Laplace transform. So C underdamped. And that is zeta less than 1, but still greater than 0, of course, because it cannot be less than 0, because all of that there is positive. Okay, after the dust has settled on the solution, we have once again the same asymptotic, so in the long term we will be charged to C times V in. No way to avoid it, after all the transients have died down, electrostatics must apply. Then 1 minus a bit of exponential has turned up xi zeta t over tau, But in front of that exponential in brackets, we have a cos of a certain frequency times t plus zeta over root 1 minus zeta squared, and the sine of the same frequency, where the frequency is once again related to zeta 1 minus zeta squared over tau. This is quite a bit to have happened, simply because we have transitioned across the sign of a discriminant somewhere. Notice that we still have an exponential fade out, so whatever transients are going to happen in that system will eventually cease, because this will disappear because of this overall exponential multiplier. We still have the same asymptotics, the electrostatic charge on the cup after everything has happened and settled down will still be the same. However, we have this transient response with some frequency that appears to be intrinsic to the oscillator circuit there, right? There is the characteristic time and there is the value of our damping parameter in the numerator here entering. Okay, let us consider the various limits and parameters here. And obscure as this might appear, this is everywhere. So this particular equation you will be dealing with until you retire, really, because systems that are either circuits of the RLC type or mathematical lookalikes of RLC circuits are as common as spin physics is in quantum theory, right? Just about anything is eventually modelable as a spin, and just about anything can eventually be modeled as some kind of RLC circuit collection. So this mathematics will be haunting you for the rest of your life, really. Okay, let us start looking at the regimes we can have here. Once again, canonical coordinates, so q of t divided by its asymptotic value, CV in, and then time here divided by the characteristic time of the circuit. There is good news here and there is bad news. The good news is if we do reduce our zeta to below 1, we can charge our capacitor even faster than that. The bad news is it will overshoot and then begin to oscillate. So if that's our 1, this is the asymptotic value of the charge, we will have the following things. So very close to 1, we would of course have the same exponential fade in. However, when we move to even smaller values, we will have something like that. And then it'll settle in, and if we reduce it even further, there will be stronger oscillations that will then likewise settle into the asymptotic value. And roughly speaking, so the yellow curve here is zeta equals 1. That is about zeta equals 0.1, and the blue is somewhere in the middle, so zeta perhaps 0.3. And the reason these are discussed so much in the literature is depending on the physical realization of this system. In this case it's RLC. In your case it will be some sequence of mixing tanks that you are adding and subtracting chemicals from, but ultimately after the dust has settled you will have a second order response function with this canonical parameterization. Here is exactly the same parameters with even exactly the same notation. The only thing that is going to change is you will have a different physics under the bonnet. I have electric electrodynamics, and you will have some concentration dynamics, pressure readings, whatever it is, but they will be mathematically the same. It's called an isomorphism, and this is very much in evidence here. Okay, there are several things that we must discuss about this curve. Firstly, well, we have succeeded in charging the cup faster, even if we end up overshooting the asymptotic charge, but this value here is called the rise time. It's the time at which we first hit the eventual equilibrium value. So that is the rise time. So do I have some specific name for it? No. I do have specific name for that. This is Q infinity, right? The asymptotic value. So the rise time is the time when the process first hits the asymptotic value. Right, so that is the first parameter. So first instance of Q inf. We might just fly straight past it on the way to a much higher charge. This is the inductor pushing us to overcharge the cup. But the first instance of Q inf is called the rise time, so the time it takes to reach that value. Time to first peak. So that is the time it takes to reach this maximum, either here or here. This rise time doesn't have a convenient analytical expression, but the time to peak does. So put it in here. That's Tp, and that Tp can be done analytically in the usual way. You just differentiate this entire beast, put the derivative to 0, find the roots of that derivative, make sure the second derivative in this case is negative, so that's a maximum, and then you get this pi tau over the same root that we've seen a few times already, 1 minus zeta squared. Okay, now the next parameter is the settling time. We really do want to know how long it takes our circuit to shake itself down to the asymptotic value, and this is defined somewhat arbitrarily as the time it takes to reach plus or minus 5% from the asymptotic value. So it time to reach and stay stay inside Q inf plus or minus 5%. And of course, because we have a decaying oscillation, that will always happen. Okay, so that is the settling time. The overshoot, we would like to know by how much we have overshot. Obviously, electrical engineers here would have to balance the response time of the circuit, right, the shorter the better, with the limits that we realistically have, because, well, that capacitor is just a physical couple of metallic plates with an insulator between them, and if we do a very serious overcharge, we will overvolt the capacitor and we will have arcing either across the insulator or through the insulator. Both are bad things because the circuit stops performing as we would like it to. Okay, so item D on the list here is overshoot. And that is actually the value of the first peak. So you find out what the first peak is and you substitute it in, and that is there. So Y max over Y infinity. So it's a dimensionless value, so we are overshooting by a certain fraction there. And that is the exponential of minus pi zeta over root 1 minus zeta squared. Okay, so then the next item is the decay ratio. And that is the ratio of the intensity of the second peak to the first. So what we've got there is it's y max 2 over y max 1. And likewise, the exponential of minus 2 pi zeta over root 1 minus zeta squared. Okay, and finally the oscillation period. You've seen here that the characteristic time is only the function of the inductance and the capacitance, but the period is also the function of how strongly it is damped once you've introduced the resistance. And so P here is 2 pi tau over 1 minus zeta squared. Once again, let's think about what is happening here. The default period is tau, and then as we are damping it more or less, we can make this period longer or shorter because, well, firstly, the capacitor takes the time to charge, and secondly, the inductor gets in the way more or less, depending on the amount of inductance that we dial. Okay, that I think is as much as I wanted to say before we proceed to the progress test. So this kind of analysis, if you look in your textbook, you will see exactly the same analysis with exactly the same notation, but for a chemical system where you are reading, I think, concentrations or pressures or something like that. To give you a somewhat less artificial example, I thought I would do it as an RLC circuit, because this is something you can literally just build on some Arduino board and watch all of this mathematics unfold in real time as you are measuring it. So we do have here standard second order ODE with the standard Laplace transform that then leads to a quadratic function in the denominator of the response function. Depending on the roots of that denominator, we either have an exponential crossfade or that kind of settling oscillation. If a certain damping parameter that we've introduced there is greater than 1, this is the overdamped mode, and you're having exponential crossfades between any changes that you put into the voltage source. And if your parameter is less than 1, then the roots become complex. You start having sinusoidal oscillations, but still settling to the same equilibrium value. Of course, it is prescribed by electrostatics, but through a bunch of bubbles. And these parameters, they are common to the electrodynamics I've described and to the reactor systems that you will have in chemistry. You have the rise time, the time to first peak, which is quite important to you chemists, because if you are reading the pressure, you really want to know what the maximum pressure is going to be and what the time is going to be to get there. These overshoot parameters will determine your engineering decisions on how much structural strength you require in there. The decay ratio is related to the settling time, right? So how long it would take either to plus minus 5% or how quickly these oscillations are dying down after you've turned that on. And finally, the period of these oscillations is also what you want to know about. Okay, that's me. Any questions?